So I've promised that we could derive the equation for the efficiency of a heat engine using the Carnot cycle, and that's what this video is about. To remind you, I have the Carnot cycle here represented on a PV diagram. It's 2 isothermal steps and 2 adiabatic steps, an isothermal compression, adiabatic compression, isothermal expansion, and adiabatic expansion. I'm also realizing I'm going to do this in black pen for better visibility, but that means no erasing, and that's super scary. So the hardest thing about this derivation is tracking signs, because we have set things up. I think the thermodynamic world is simpler when we take the perspective of the system, and in this case we have to take the perspective of the human. So as humans, we're going to define efficiency as the net work that we get out of the system. So during these compression steps, we have to put work into the system, and we want to subtract that from our net work. We want to account for that. So it's net work that we get out over the amount of heat that we had to put in. And again, these quantities are taking the perspective of the human. So let's take a minute to make sure that we can track from the human's point of view which way energy is flowing in each of these steps. So I'll tell you to pause the video here. And actually, I encourage you to think about both the system and the human and see if you can track which direction energy flow is in the form of heater work for each of these steps. All right, so if I track, I'm going to write down my tracking of those parameters. So let's think about systems. Let's represent that by our frictionless massless piston and humans. So for step 1 to 2, which is the isothermal compression, the human had to put work into the system to do the compression. In this case, heat flowed out of the system, but the human doesn't really care, because they're going to, in most engines, they're going to dump that heat to the environment. So the exhaust gas of your car gets dumped to the environment. The cooling water on a nuclear power plant that sits on a river gets dumped to the river, and the human doesn't have to do any work for that. The exhaust steam from a steam power plant, well, lots of it gets recollected, but there's closed water circulators that can sometimes exhaust steam into the atmosphere. But generally, this heat dissipation into the cold sink, the human doesn't really care about this. For 2 to 3, the adiabatic compression, the human again has to put work into the system. And there was no heat flow. So again, the human probably does not very much care. For 3 to 4, the isothermal expansion, this is the step that the human finally gets work out. But he also, for this step, had to put heat into the system. So if he was driving a steam engine in the Industrial Revolution, that means the human is shoveling coal or doing something of that nature. So the human in this case is also a little sad because he's having to do work. For step 4 to 1, the human is still getting work out. And because Q is equal to 0, it's adiabatic. The human does not really care. about the heat flow in that step. All right, so now that you have a sense of which direction energy is flowing, I'm going to not quite cheat, but take the easy way out of calculating efficiency. And the way I'm going to take the easy way out is by making shameless use of absolute value signs. So if I go to calculate the efficiency, remember it's net work over the heat that the human had to put in. And the net work that we get out is going to be positive for the 2 expansion steps and negative for the 2 compression steps, or that's the way I'm going to want to account for it. And I can force that accounting by using absolute value. So I'm going to take the absolute value of my 2 expansion steps and then subtract the absolute value of my 2 compression steps. You don't have to do it this way, but this is just the way I found it easiest to keep track of signs. And then we're dividing by the magnitude of the heat that we had to put in during that isothermal step. So at this point, I recommend pausing again. And make sure you can derive the equations for each of these terms. Okay, so I'm not going to derive each of the equations, but I wanted to make sure that as I do this derivation, I write out the equations that you know where they come from. So you'll see the equations as we go along. So let's first look at steps 4 to 1 and steps 2 to 3, our 2 adiabatic steps. The work for an adiabatic step is equal to CV times the difference in temperature. I should say that a thing I'm going to do is, even though we have state 1, 2, 3, and 4, we only have 2 temperatures in the system. We have a cold temperature and a hot temperature. And so the simplifications I make in the equation are easier to see if I just denote the 2 temperatures in terms of whether they're the cold side or the hot side. But this equation would be CV T1 minus T4 and CV T3 minus T2. And then you can just check that the third state is at the hot temperature and the second state is at the cold temperature. And I'm going to do that throughout this derivation. All right, so this term is equal to the negative of this equation, or that equation is equal to the negative of this equation. And so what you can see is that the magnitude of these quantities is going to cancel out. So those 2 terms cancel each other. So from there, I can write that the efficiency is the work of my 2 isothermal steps divided by the heat input of the hot side isothermal step. You may also recall from your derivations that you did during the pause that these 2 are actually opposite of each other, so they take the opposite sign because the internal energy is equal to 0. So when we take the absolute value, the magnitude of these 2 quantities stays the same. So I can simplify this equation as follows. And then if I write out the values for the 2 terms I have left, I get this. Okay, so now my challenges to pause, and I'm going to say use, we're going to have to simplify this part, this term here. So to do that simplification, my hint is to use adiabatic relationships and you have two adiabatic relationships between states 2 and 3 and states 4 and 1. So use equations for these relationships to show that V2 over V1 is equal to V3 over V4. All right, here's how I get there. If I write out the equation for the adiabatic relationship between states 2 and 3, I get CV, natural log of TH over TC, equals R natural log of V2 over V3. I also get CV natural log of T hot over T cold equals R natural log of V1 over V4. So if you notice, I have the same term on the left side of these two adiabatic relationships, so I can equate these two terms. So I get R ln V2 over V3 equals R ln V1 over V4, and because the prefactor is the same and it's the same natural log, then I get to say that what's inside these parentheses are equivalent. So from here I get V2 over V3 equals V1 over V4. And I can just rearrange this to V2 over V1 equals V3 over V4, as we asked you to show above. So what this allows me to do is to substitute V3 over V4 in this quantity of the natural log up here. And what I could do is I could switch the sign of this natural log and get a negative, pull out a negative, but because I'm within an absolute value, it doesn't matter. Basically, the quantity of these natural log terms is the same, so they'll cancel each other, and the r's will cancel each other. So I can simplify this equation to 1 minus Tc over Th. And the conclusion that we can draw from this then is that for the Carnot cycle, for our Carnot heat engine, that the efficiency of the engine doesn't matter on anything about the scale of the system. It doesn't matter, the compression ratio doesn't matter. Nothing matters except for the ratio between the temperature difference between your hot side and your cold sink. We'll show in the next video that even though we derived this using the Carnot cycle, we'll show that this is the maximum theoretical efficiency for any heat engine. All right, see you next time.